Okay, so this is part 4 of Unit 2, and we are going to be looking at zeros of polynomials. So this whole video is just going to be about how to find the roots, or the zeros, or x-intercepts, again, those all mean the same thing, of a polynomial. So first we're going to find the possible rational roots. And what we mean by rational numbers, remember that's a number that can be written as a fraction. But then we're going to move on to actually finding what the roots are. So first we're going to list the possible ones using the rational root theorem, or the rational zero theorem. And what we're looking at is, again, this is the general form of a polynomial. We're going to be looking at the factors of the constant over the factors of the leading coefficient. And those will give us all of our possible rational roots. So again, one of the roots that can be written as a fraction. This does not tell us what the possible imaginary zeros are, or what the possible irrational roots are. Those always come in pairs, and we'll see how to find those later on. So first off, listing all the possible rational zeros. In this case, my constant is 4, and my leading coefficient is -1. All of the possible factors of 4 are positive or -1, positive or -2, and positive or -4. All of the possible roots of -1 are positive and -1. And we'll always use that plus or minus sign, including both the positives and the negatives. So we have to create every combination here. So 1 over 1, 2 over 1, 4 over 1, and that would just give us plus or minus 1, plus or minus 2, plus or minus 4. The next example, our constant is -2, and our leading coefficient is 15. So if I'm listing all of the possible rational roots here, I need to think about the roots of 2, which are 1 and 2. And then I need to think about the roots of 15. So that would be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So all those combinations, 1 over 1, 1 over 3, 1 over 5, 1 over 15, 2 over 1, 2 over 3, 2 over 5, 2 over 15. So that would then be plus or minus 1, 1 over 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1/15. Then 2 over 1, plus or minus 2, plus or minus 2 over 3, plus or minus 2 over 5, and plus or minus 2 over 15. Okay. And if we got numbers here, like let's say I had, I don't know, 2 over 6. Well, that would reduce to 1/3. I don't need to list it twice as long as it's listed once here. So the next type of example we're going to look at here are, once we use the possible zeros, then we can use them or test them using synthetic division to find which ones actually are roots. So these are all of our possible roots. I want to use all of the possible roots to find what are the actual roots. And you're going to have a total of whatever your degree is. So if the degree is 3, you're going to have a total of 3 roots. So again, plus or minus 6 over my leading coefficient, which is plus or minus 1. So that'll be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So that's 8 numbers there that I could check. So that would be plugging in f of 1, f of -1, f of 2, f of -2. I can continue to go on and on and on, and we can go ahead and plug those in. If I plug in 1 cubed is 1. And then plugging in 1 again, 1 squared is 1 times 2 is 2. Plugging in 1 here, minus 5, and then minus 6. Well, that's not equal to 0. So if I want to figure out whether something is a root or not, what I'm using here is called the factor theorem. That was in the last video. And if I plug in this value and it equals 0, that means it is a root of this polynomial, and then I can use synthetic division to divide. So I'm going to keep plugging in these values until I get one that equals 0. Well, plugging in -1, -1 cubed is -1, -1 squared is 1, times 2 is 2, minus plugging in -1, -1 times -5 is plus 5, minus 6. -1 plus 2 plus 5 minus 6 does equal 0. So we found one that works. Now I always like to kind of write my answers off to the side here. I know I'm going to have 3 answers because, again, it's degree 3. And I just found one of them. One of them is -1. So what I want to do at this point is rather than continuing to plug in things, I want to use synthetic division to divide. So plugging or dividing by -1, my coefficients here are 1, 2, -5, -6. Again, bring down the 1. -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. -5 plus -1 is -6. -1 times -6 is +6, and those add to 0. And again, if your remainder is 0, then that means it does divide evenly. So what I'm left here is constant x value, x squared value is x squared plus x minus 6 equals 0. Well, that's a quadratic equation. We could use the quadratic formula, we could use the x method, we could use any of our 4 methods for solving quadratic equations. If I use the x method, I'm going to get x plus 3 and x minus 2. And that gives me my last 2 roots. So I have all 3 roots now. Let's do another example. Here we have x cubed plus 7x plus 11x, or 7x squared plus 11x minus 3 equals 0. So again, it's degree 3, so I know I will have a total of 3 roots. And my constant on the end is -3. My leading coefficient is 1, so plus or minus 1 and plus or minus 3. I only have 4 numbers that I can check, and so what we can do here then is just start plugging them in. F of 1, f of -1, f of 3, f of -3. Now I'm not going to show my work for all of these just for the sake of the length of the video here, but I can tell you if I plug in 1, it's not going to be equal to 0. And you can go ahead and check that. Go ahead, take a minute, plug it into that, and see that it does not equal 0. In fact, the first 3 of them will not equal 0. So again, check that I'm right here. Plug those in. You can pause the video, plug them into the equation, and see that they don't equal 0. But this one does. So I know that -3 gives me one of my roots. So dividing by -3 using synthetic division, 1, 7, 11, and -3. Bring down the 1. -3 times 1 is -3. 7 plus -3 is 4. -3 times 4 is -12. 11 plus -12 is -1. -3 times -1 is 3, and that adds to 0. So I'm left with x squared plus 4x minus 1 equals 0. And I could try the x method all day and it's not going to work. So I can go ahead and just try the quadratic formula then. -4 plus or minus the square root of 4 squared is 16, minus 4 times 1 times -1, all over 2 times 1. So, simplifying that, -4 plus or minus the square root of, a negative times a negative is a positive, 16 plus 4 is 20 over 2. 20 we can simplify. And again, you need to simplify these as much as possible. 20 is 4 times 5, so that's 2 root 5 over 2. 4 and 2 can reduce here, so I can simplify that to -2 plus or minus square root 5. So I have -2 plus square root 5 and -2 minus square root 5 as my last 2 roots. Okay. All right, and flipping to the next page here, we've got one more example of this, or of this topic here. And here we have a polynomial of degree 4. So that means that we are going to have 4 answers. Okay, so I know I'll have 4 of them. And my constant on the end here is 24. My leading coefficient is 1. So 24 has a lot of factors. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and then plus or minus 24. So that would be a lot if we plugged all of those in. I'll tell you right off the bat, again, I've done this ahead of time, so I know which ones work and which ones don't. Plugging in 1, -1, 2, -2, and This one does not equal 0. Oops. It's not equal to 0, not equal to 0, and plugging in 2 does equal 0. So we can go ahead and divide. So putting 2 in the box there, and we can go ahead and plug or use synthetic division here. We don't have an x cubed term, so remember we need to use a placeholder there. Bring down the 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 6 plus 4 is negative 2. 2 times negative 2 is negative 4. Negative 8 plus negative 4 is negative 12. 2 times negative 12 is negative 24, and that adds to 0. So we know 2 works. We can go ahead and put that in our box there. And what I'm left with here is a cubic polynomial. Now that has 4 terms, and so if I could, I would think maybe using the factoring by grouping, but it's not going to work. And in fact, if I plugged in the rest of these numbers, none of them work. There's not another one. I could spend the rest of my time here on this video plugging in, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. None of them will equal 0. So if that happens, there's a couple of possibilities. It's possible that the remaining roots are imaginary or irrational, but we have 3 roots left, and we can't have an odd number of imaginary or irrational roots. You'll always have an even number of them. So what that means is then maybe this has a multiplicity of 2. Maybe it's possible that we could divide by 2 again with our smaller polynomial here. So now I'm not using those same numbers up here. I'm using the smaller polynomial here. 1, 2, negative 2, negative 12. And we'll try dividing again to see if we have a multiplicity of 2. Bring down the 1. 2 times 1 is 2. 2 plus 2 is 4. 2 times 2 is 8. Negative 2 plus 8 is 6. 2 times 6 is 12. And that does add to 0, which means that it is in fact divisible by 2 again. That means another one of our roots is 2, has a multiplicity of 2. And what we're left here is a quadratic equation. And we can go ahead and use the quadratic formula for that. So x equals negative 4 plus or minus square root of 4 squared, which is 16, minus 4 times 1 times 6, all over 2 times 1. 4 times 6 is 24, and 16 minus 24 is negative 8. So negative 4 plus or minus the square root of negative 8 over 2. And the first thing we should be thinking is a negative inside the square root means we're going to have an I that gets pulled out. But also 8 we can simplify to 2 root 2. So negative 4 plus or minus 2I root 2 over 2. Again, 8 is 2 times 2 times 2, so I could pull 1, 2 out, and 1, 2 stays in. And then the I comes out because of the negative. We can simplify this one step further. 4 divided by 2 is negative 2. 2's cancel, and we have plus or minus I root 2. So my last 2 roots are negative 2 plus I root 2 and negative 2 minus I root 2. Okay. All right, we have one more example in this video here, and it's going to be going the opposite direction. I'm going to tell you what the roots are, and you're going to need to come up with the original roots, or the original equation. So if we have a 3rd degree polynomial here that has real coefficients that have negative 3 and I. Oh, you know what? There's one thing before we go into this example here that I want to go over. These are other pieces of information that are important about finding roots. So this is kind of what I've been talking about with the irrational and imaginary roots. If you have irrational zeros, meaning decimals that go on forever that have no pattern, so like pi, e, square roots of numbers that are not perfect squares. If you have this as a root, then you also have its conjugate. So if I had, let's say, 2 plus square root of 5 as a root, then I also have to have 2 minus square root of 5. They have to come in pairs. So if this is one of my x values, this is also one of my x values. Same thing with imaginary roots. They also come in conjugate pairs. If you have a plus bi, then you also have a minus bi. So again, for example, let's say I had -3 plus 4i as a root, then I also have -3 minus 4i as a root. They always come in pairs. So you will always have an even number of imaginary roots and an even number of irrational roots. It could be that you don't have any at all, but if you have some, it'll always be an even amount. So in this last example here, it says find a third degree polynomial with real coefficients that has 3 and I as zeros such that f of 1 equals 8. So we know that x equals -3, we know x equals I, and if x equals I, then x has to also equal -I. They always come in pairs. So even though the instructions didn't say that, we do know that these come in pairs. So if I have I, then that means I automatically also have -I. So those are my 3 roots. And we can go ahead and write our function out like this. X, and then -3 means it'll be x plus 3. Again, if I set that equal to 0 and solved, I'd get -3. X minus I and x plus I. Now, I don't know what the leading coefficient is, so we're going to use A to just represent whatever that leading coefficient is. Now, I'm going to go ahead and do some boxes off to the sides here. I'm going to multiply out, because I need to multiply all these out. I'm going to multiply these two first, x minus I and x plus I. This is x squared minus xi plus xi, and then minus I squared. But remember, I squared is equal to -1. So -1 times a negative equals 1. And notice, positive xi, negative xi, those cancel out. So this becomes x squared plus 1, this whole thing here. And then x plus 3, and then a equals f of x. All right. And from there, now I'm going to go ahead and multiply these two out. So I have x squared plus 1 and x plus 3. That'll give me x cubed, x, 3x squared, and 3. So then this becomes f of x is equal to a times x cubed plus 3x squared plus x plus 3. And now our goal is to find this a value, and that'll give us our equation. So from here, we can go ahead and use this piece of information here. This is my x value, this is my y value, or my f of x value. So 8 is equal to a times, and I can plug in 1 for x. 1 cubed is 1, plus 1 squared is 1 times 3 is 3, plus 1 plus 3. Well, 1 plus 3 plus 1 plus 3 is 8, so 8 equals 8a. Dividing by 8 on both sides, a is equal to 1. So if I were to distribute a 1 on this whole equation, I would just have what's here. So f of x is equal to x cubed plus 3x squared plus x plus 3. If I had another a value here, like let's say I got a equals -2, then I would distribute a -2 onto this whole thing, and that's what f of x would be. And that is going to bring us to the end of this video, and then we'll pick up with rational functions in the next video.